It's hockey time. Hockey puck A travels on smooth ice at a speed v and collides with hockey puck B at rest. Puck A goes off at speed v/2 at an angle of 60 degrees with respect to its original trajectory. What is the speed and recoil angle of puck B, and is this collision elastic? Maybe the first thing to do is think about what happens in a collision. We have two pucks, and let's just talk about what happens at the moment that they collide. We can discuss the forces that each one feels. There's a force of gravity acting on each puck. There's a normal force coming up from the ice. And there's also a contact force. The first puck pushes on the second puck pushes on the first puck. If we get to neglect friction, then when we think of these pucks as a system, which we can sort of wrap in this purple rectangle that I've drawn, we can say that this system is effectively isolated in the sense that the net force acting on this system, which I'll say that as the net external force on that system, is equal to 0. And if the net external force on a system is equal to 0, that means that momentum is conserved. And so I will use conservation of momentum as one of the key concepts for solving this problem. Before we go any further, though, let's draw a little picture to give us some help in seeing what's going to happen. Puck A starts off moving, and it's moving at a speed v. Puck B is like this with its initial velocity of 0 because it's at rest. Afterwards, puck A is going off in this direction. It has a final speed of v/2, and puck B is going this way, and we don't know what puck B's final velocity is. So I'll write it as vb prime. To help our eye identify where the angles are, let me indicate what the original trajectory of puck A was and point out that it is this angle here, theta, which was 60 degrees. Meanwhile, this angle here is something we're going to try to figure out, and that is phi. So the two unknowns for us at the beginning here is to figure out what is the speed of puck B and what is the angle phi. We're going to try to use conservation of momentum to solve this problem. One last point is that these are hockey pucks. We'll assume that they have the same mass, and with any luck, we won't actually need it. Conservation of momentum is a concept, but it involves an equation. Conservation of momentum says that the initial momentum of a system, the entire system, is equal to the final momentum of that system when you add up all the momenta of all the constituent particles. It's a vector equation, which means it holds in the x direction and in the y direction separately. So we will apply them in the x direction and see what we get. In the x direction, at the very beginning, we can see that the momentum is the mass of the puck times v. The entire velocity is in the horizontal direction. Here's a coordinate system in case we need it. In the end, what we have is puck A going off at some speed of v/2, so it has a component mv/2, but we have to include that angle to get the horizontal component of that velocity, so we have to use the cosine of 60 degrees. Then we can include the x momentum of puck B, which is its mass, its speed, and we have to use the cosine. That's the cosine of phi. Notice that there's an m that appears in all of these terms, and so it actually doesn't matter what the mass of the puck is. So we can clean that up. We can also remember that cosine of 60 degrees is equal to 1/2. And so at this point, we have learned that the initial speed v is equal to v/4 plus vb prime times the cosine of phi. In the y direction, we'll have a similar idea. The initial y momentum is 0. And that's because initially the puck is only moving in the x direction. Afterwards, as we've drawn it, the y momentum of puck A is mv/2 times the sine of 60 degrees. To figure out what's going on with puck B, we need to make a convention. Let's choose by convention that phi will be a positive number. We'll just take the magnitude of that angle. In order to account for the fact that puck B is going in the negative y direction, I will include that with a minus sign explicitly here and write m vb prime times the sine of phi. Just to be very explicit, we're by assumption assuming that phi is chosen by definition to be greater than 0, and this minus sign does what we want it to do. Once again, the mass appears in all of these terms. Sine of 60 degrees is the square root of 3 over 2, and so we learn that 0 is equal to square root of 3 over 4 times v minus vb prime times the sine of phi. Now, we have a number of options here. If the first thing we want to do is solve for vb prime, then maybe what we should do is take this equation 1 and this equation 2 and solve for vb prime. Let's see what happens when we do that. Equation 1 rearranges to look like this. vb prime cosine of phi is equal to 3/4 times v. And then we can use equation 2 to solve for vb prime sine of phi. That is apparently square root of 3 over 4 times v. Now I'm going to use a trick that has to do with the squares of cosine and sine. Let's do that on the next page. You may or may not remember that the cosine squared of phi plus the sine squared of phi is equal to 1. And that's a useful trick in this situation because as what we're trying to do is figure out what is the magnitude of this vector vb that has components vb prime cosine phi and a vertical component which has a magnitude vb prime sine of phi. So what that means is that to get the magnitude of vb prime I should say, we are just going to take the sum, the square root of the sum of the squares of its side lengths. In other words, this would be vb prime cosine of phi squared plus vb prime sine phi squared. And the fact that the sum of cosine squared and sine squared is equal to 1 is one quick way to see how this absolutely must be true. But using what we just learned on the previous slide, vb prime cosine and vb prime sine, this is the square root of 3/4 v squared plus the square root of 3 over 4 v squared. And when you work that out, this comes out to be 9/16 v squared plus 3/16 v squared. And if we clean this up just a little bit, we'll discover that this is the square root of 3 over 2 times v. So that is the answer to that first part of the question. What is the speed of puck B when it recoils? Square root 3 over 2 times v. Now, what is the angle? That is something that we could work out in a number of ways. We have already seen that there is some relationship between vb prime and cosine of phi. We could do it with that, or we could do it with sine, or we could do it with tangent. Just to mix things up a little bit, let's do it with tangent. The tangent of phi can be written as vby, the magnitude, divided by vbx, the magnitude. Why am I saying magnitude? Because if we go back to our picture, we have these side lengths, and I'm not going to worry about whether one is positive or negative. I just want to know the absolute value of that angle. When I do this, I will learn that this is actually the square root of 3 over 3, and when you do the inverse tangent, phi is equal to the inverse tangent of square root 3 over 3, and you get that this is 30 degrees. So that is our angle. 30 degrees. Lastly, is this collision elastic? The way to check for that is this word elastic means is conservation of energy obeyed? And to do that, we would check to see if the initial kinetic energy, 1/2 m v squared, is this in fact equal to the final kinetic energy, which is 1/2 m, the final speed is v over 2 squared, plus 1/2 m, the final speed of puck B, we learned that was square root 3 over 2v squared. And we can ask, does that equality hold? And it does, yes. So conservation of energy does hold, and therefore this is an elastic collision.